Yes, this is joint work with Andreas Maurer. So the goal of this work is to extend the method of Rademacher and Gaussian averages from linear statistics to nonlinear statistics. So let me first recall the standard result. So we have a vector of independent random variables, x1 through xn. And we have a space of functions, for example, linear functions. And then the goal is to study this empirical process, so to bound the expectation of the supremum between the empirical and the true mean. Okay. So it turns out that if we have a bound on this empirical process, then we can get generalization bounds using the bounding difference inequality. And a standard trick, the symmetrization tricks, bound the empirical process by the Rademacher average. So this is a result that everybody knows. It's very simple and very useful. To prove this, you take outside this expectation, and then you observe that if you exchange a component of x with a component of x prime, the result is invariant under this change. And then you introduce the Rademacher variables and then Rademacher complexity. The same result holds for the Gaussian complexity. And so this has proven very useful because there are, in the past years, there have been a lot of results bound the Rademacher complexity with several applications in statistics in machine learning, so from kernel methods to also unsupervised learning, dictionary learning, multitask learning, matrix learning, etc. So this result is very popular and has proven very useful. So the goal of our work is to study similar results in the case in which the function f here, so the function f here is empirical average, right, is replaced by a nonlinear statistics. So for example, a U statistics or some L statistic which involves some order statistics, and so on. Okay. So to introduce, to present the result, we require some quantities, and we require some semi-norms which measures the dependencies between the variables for the functions f. So, so in general, we consider a function f from un to r, where u is a subset of rd. In the previous slide, it was the unit interval. And then we recall the k partial difference operator, which, like in the case of McDiarmid inequality, the bounding difference inequality, looks at the difference of the function f when you perturb one component. Okay, so here you have the same argument except for the k component, which is y. Here is y prime. And these coordinate-wise Lipschitz semi-norms, they are of the first and the second order. And the first order one looks at the maximum value that of the k partial difference operator normalized by the degree of perturbation that you make. So that's why we call it Lipschitz semi-norms. And the second order one looks at the second difference. And it looks at interaction between two different components of x. Okay, so here k and l are different coordinates. And also here we put n because, as we will see, so this ensures that in our bound these two semi-norms appears in the same order. Okay. Now, if you recall the case in which f is the empirical sample average, then it is easy to see that the first order semi-norm is 1 over n or 2 over n, and the second is 0. So the second order semi-norm somehow measure the distance of our function from the subspace of additive functions. Okay, so this is very important in our result. And so here is the result. So if you compare to this result here, where you have 2 over n times the Rademacher average, so our result contains the Gaussian average instead of the Rademacher average, and it contains these two semi-norms here, right? Now, whenever the semi-norms are of order of 1 over n, the bound is tight. In particular, for the sample average, as I just said, the first order is 2 over n, the second is 0, and so we essentially recover the standard results up to a factor of 2, right? We recover the standard results for the Gaussian average up to a constant factor of 2. Also, the results all in the other direction because the semi-norms are symmetric to change of sign. And again, using the bounded difference inequality, we can get tail bounds. And finally, as I mentioned, the result holds for the Gaussian average, but in many practical cases, the Gaussian average is of the same order than the Rademacher, and even the worst case is just a little bit worse, so this is not a major concern. So we have a number of applications of this result. I will just discuss briefly one and mention a few others. So one application is to the case in which our nonlinear statistic is the area under the curve, or bipartite ranking. So in this case, our random variables, we assume that n is even, and we assume that the first n over 2 component of x are sampled from IID from some distribution, and the remaining one IID from another distribution. So this will be the positive and negative class. And then we consider as our nonlinear statistics the sum of all the possible pairs from positive and negative distribution of this loss function. Okay. So if the loss function is a 0-1 loss, what the nonlinear statistic measure is an empirical estimate of the area under the curve. And then if we replace the loss function by a Lipschitz loss function, then we can show that the Lipschitz semi-norms are of order of 1 over n. So our nonlinear statistics is weakly interactive. And then our theorems then gives uniform estimation bounds for area under the curve maximization. So in this case, for example, the class of functions H could be a subset Boltzmann reproducing kernel Hilbert spaces. So in the paper, we have more general applications. So one is about U and V statistics. So the one that I just described is second order U statistics, but our results also hold for higher order U and V statistics with component-wise non-symmetric and non-uniform kernels. And another application is to Lipschitz L statistics. So this will be some linear combinations, smooth linear combination of the order statistics. So this, for example, can be used for robust learning when you want to remove outliers, and then instead of computing the empirical mean, you compute a weighted mean in which you remove, you downsample the large losses. And finally, another application that we described is M statistics with strongly convex objectives. For example, the error of ridge regression, so the empirical error of ridge regression, this can be seen as a nonlinear statistics. And then so in all these cases, we show that the functions are weakly interactive. And so therefore, our results allows us to get uniform bounds and also tail bounds almost as a plug-and-play way, because we already knew the bounds for Gaussian averages, and then by bounding the semi-norms, we readily have bounds for this nonlinear case. Yeah. Yeah.
Do you have questions?
There. Yeah. Well, there are many bounds for the Gaussian average, many bounds for the Rademacher, and yeah. So, I don't know. I mean, You can use the result in either case because the Gaussian average is bounded by the Rademacher average. So.
Do we have any more questions? If not, we can thank the speaker again. You can either use that one.
Which one?
You can either use this mic or this one, whichever.
Yeah, I can use this one. Do you have the
It's here.
slides?
Yeah, it's right here.